New from ESCO Institute. This is what people are saying about the ESCO EPA Section 608 online interactive course.
Great presentation and understanding of materials. The clarity of topics are consistent, which helps the learning process immensely.
The flashcards, along with the excellent graphics and clear instructions, are fantastic.
I took the 608 core test before I came here and got 45%. After taking the ESCO course, I passed with 85%.
Do you need to get 608 certified? You will find the ESCO EPA Section 608 interactive course on the HVACR Learning Network. The HVACR industry's leading source of online and digital content. Visit us at hvacr.elearn.network.
All right, everyone. Thank you so much for joining. Did you know the ESCO HVAC show? How could you not have fun when we start the show out with an intro like that?
It was pretty cool.
That was a lot of fun. Chris Mohalley, thank you so much for joining us once again. We are on part 3 of a 4-part series on motors, right? So we've dove through ECM constant torque. We went through ECM constant airflow. We're going to spend a little bit of time on ECM condenser motors because we're seeing a lot more ECM motors on our outdoor units. All right, so let's take a little time today and get a little deeper on ECM condenser motors.
Sounds good. I guess that's my cue.
That's you.
So direct drive outdoor fan ECM motors. We're going to talk a little bit briefly about when they began to become integrated into the industry, where you're likely to see them, why you may or may not be seeing them in your market, why you may or may not start to see them in your market in the near future. We, Gentech, again, formerly branded GE Motors, we introduced the ECM outdoor fan motor around the year 2000. And they're predominantly used in 16 plus SEER systems. So I do know there's some manufacturers that use them in 15 SEER, but predominantly across the industry starts at around the 16 SEER rating and up. Obviously, you know, there's a difference. The OEM has to weigh the value of energy efficiency versus cost of the motor, you know, to other components or changes they can do to hit those SEER points. So around 16 SEER is where we typically see these motors. Used in applications, again, to achieve SEER ratings today that are basically higher than the minimum requirement for most regions of the U.S. And we'll cover that a little bit in a moment. But I wanted to hit that first, again, introduced in 2000. So real quick history lesson. This won't take very long.
Yeah.
I don't know if you were, you know, I was kind of a history nerd in school. Everyone may not be, but this won't be as cool as, like, you know, World War II or something like that. So go back to 1999, and you know, about 100% of new equipment built was still using PSC motors, PSC direct drive, shaft up, shaft down, outdoor fan motors. And again, we introduced the ECM in 2000. So if you fast forward to 2022, 22 years later, if my math is correct, about 15% of the industry has shifted to using ECM in their outdoor fan motors, and that may be closer to 20% by now.
Yeah,
but again, depending on where you are, so if you're in the southern or coastal regions of the U.S., you probably see more units that are 16 plus SEER. If you're where I am in the central U.S., I'm in Wisconsin, by the way, if I haven't said that in previous webcasts, we don't see a lot of 16 plus SEER systems because the efficiency versus the usage just doesn't rate the cost of the equipment in our market. So again, reminding you that these are predominantly used in 16 plus SEER systems. You know, 2006, we saw the 13 SEER regulation. 2015, it went up to 14 in the middle U.S., 15 in the southern and coastal regions. And I believe in 2023, that didn't change, unless I am mistaken. I'll lean on you for that to agree or disagree. So, you know, we're still seeing that the ECM outdoor fan motor is used in equipment that's above the minimum SEER rating. Why is that important? Well, it's not necessarily being regulated in, it's manufacturers that choose to build higher SEER systems for those regions that can benefit from, the higher efficiency. Whereas, my region, 95% two-stage gas furnaces are very common, not very common in the southern and coastal regions where they don't have as much a need for a heating demand. So does that make any sense? Do you have any questions on that? Anything to add, Clifton?
No, not really. And we have a whole nother show where we talk about the SEER2 side of things and changes in regulations. And I'll put a marker up for that in the video later. It'll be
That's good.
cool up there, and we'll direct you over to some deeper SEER2 regulation stuff. But yeah, just for what we're talking about, the reason that we're going forward with so many ECMs is to maintain efficiency of systems, especially our two-stage and our variable capacity systems.
Yep. And there again, just because if I'm correct on where our regulations are today, if those regulations change and we do hit 16 SEER, then wherever that regulation changes in, whether that changes in all of US or in the southern and coastal regions, we may start to see more of those motors in those areas.
Absolutely. And that's the reason we do these classes, is so that everyone is aware that, we are continually making advances and transitions in technology for our equipment. And so we have to be prepared for the things that we're going to be encountering more and more and more often. And everyone that's joining us, we really want to know where you're chiming in from. So let us know in the chat, and we'll make sure to share with everyone so we can see how big our village, our community of HVAC and building professionals is growing.
There you go. So again, just a little bit of an overview. These motors are found in residential and light commercial, 5-ton or less HVAC applications, typically 15 or 16 SEER and above. Now, these motors could be either multi-speed or communicated, and we will dig a little deeper into both of those so you understand what we mean by multi-speed or communicated. And they are, like all other ECMs, OEM configured, meaning they are programmed by the manufacturer to operate at the speed or speeds that the manufacturer needs for their single or two-stage equipment. So these motors do have a 600 to 1200 RPM range. In other words, the way we build them, they're capable of operating between 6 and 1200 RPMs, and that's because they were originally designed to replace the 6-pole 1075 and the 8-pole 850 or 875 or 825 RPM PSC motors. So, we designed the ECM to replace what was existing in the equipment at the time. And, the OEM may program, when I say OEM, I mean the HVAC manufacturer. Right. They may program that motor to run at 825 or at 1075, or as we're seeing today, they may choose to let the blade engineer develop, some kind of blade that's very large and very odd looking, but moves the same airflow at a lower RPM, so we get less decibels, less noise out of the equipment, and then they can program that motor to run at any RPM they want. So they can program that motor anywhere from 600 to 1200 RPM. Just because there may have been an 8-pole PSC in that equipment previously doesn't mean they're going to use strictly 825 or strictly 1075 if it was a 6-pole. And we'll talk about a little bit more as we go through the presentation as well, because it's very important to understand that these constant airflow motors do not have fixed 1075 or 825 RPM operating points like the PSC motors that they replaced. Okay, so another interesting note about these motors is they may look a little different depending on how they're applied. Are you waving at me or somebody else?
Tom Tebby joining us. No.
Hey, Tom.
Tom Tebby. Thank you.
So when they're built for shaft down, they look a lot like the ECM motors we see in indoor blower motor applications, where the motor control is bolted onto the back of the motor. It is bolted onto the back of the motor in the same fashion, where the molded portion is facing up. And we see that here, so that when the rain hits that, it runs off that molded portion. It's going to run down past this seam. These seams are typically not sealed. The water's allowed to run by it. Very unlikely it's going to wick back up into that electronic area. And that's going to be the typical design of a shaft down application. In shaft up, shaft up is the motor I get the most phone calls about. One, they ask, why don't we put handles on all of our motors to make them easy to carry? That's not a handle. And two, they're curious why the control seems to be flipped over. So in a shaft up application, we do flip the control over. The
Yeah.
umbilical cord that would normally be in between the two motor and control that you normally wouldn't see
Yep.
now exits the bottom of the control through a dust cover and then enters through the side of the motor. And that's what that, people call that a handle. That's the umbilical cord that you normally don't see. And we do that again so that that molded portion of the can is facing up so that water can run off that. We don't have a, if we left it mounted this way, we would have a seam between the motor and the control where water could come in and literally pool inside the control. By flipping the control, now that water runs off again, very unlikely. All that's on the bottom of that is simply a dust cover. And, it's very unlikely that water is going to collect in there and pool back or wick back up to the electronic control.
And I've seen this design, and every time I look at it, I go, okay, let me look here. What am I seeing? And I kind of recognize that our control was configured different, and now it makes complete sense.
Yep,
So
yep. So if you see that little jug handle, that usually means you've got a shaft up motor and the control was flipped over on purpose.
Yep.
And then last but not least, another design which we call the remote located or remote control. So the control is not mounted. I call it, maybe it's not the correct terminology, I call this locally located. The control is located locally on the back of the motor.
Sure.
And this is a remote located control. So you can see in the unit here, the motor is mounted where it usually is. And then instead of the control being on the back of the motor, the wires go down and they go to the control, which is remotely located. So this is that umbilical cord that, again, if you've never seen a remote located outdoor fan motor, or you've never seen a remote located indoor blower motor, that umbilical cord is always hidden between the motor and the control. In this case, it's a longer umbilical cord. It's shielded because there is electromagnetic interference that travels through those wires. We don't want that to interfere with anything in the house or around, or them to interfere with the motor. And then we've got the wires that we would normally see connected to the contactor, the circuit board, coming out of control, and those go into the control panel. What's funny about this configuration is if the technician isn't paying attention, they may simply think that that's a PSC motor because it looks like a PSC motor. There's no electronic control on the back of it. And if you don't follow those wires down and see that controller, if you take the panel off and just start, I've got 230, it should be running, you'll miss the fact that this is an ECM and it operates a little differently. So worth looking inside and looking for those added components.
Yeah, absolutely. And I have encountered these in the field, and, particularly on units that have a more narrow venturi on the top cover where they can't use an extended length motor. They're able to use that remotely mounted control. So they are out there.
Yep. And I have plenty of speculations as to why some OEMs do and some OEMs don't. Sometimes I see these on really large systems, and I've speculated that they can't handle that extra weight out in the middle of that long expanse of cover, because it might make it bow a little bit or vibrate during operation. I used to think that it was because of distance, for clearance between the end of the shaft and the compressor, but most of these systems are taller than my car these days, so I don't think that's the case.
20 SEER,
Right, exactly. So that's just a little bit of background on why you'll see this motor built in different orientations and what it looks like. The motors themselves, if we're talking strictly about residential like commercial applications, they're typically built for 208, 230 volt. They could be operated or energized or commanded with either 24 volts AC or some form of DC voltage, which again, we'll take a deeper dive on that very soon.
Okay.
That's OEM specific, and the RPM that it operates at, the speed that it operates at, is OEM specific. If I didn't mention, and this is very different than our indoor blower motors, this is a constant speed motor. So this motor doesn't care about how much torque it's operating at. It doesn't have a constant airflow algorithm. It's just told to operate at a given RPM, and that's all it does. It operates at that RPM all the time. Doesn't try and speed up or slow down to maintain an airflow operating point. All it cares about is maintaining the RPM of that shaft at whatever it's programmed to operate at.
Are we using back EMF to calculate that?
What's that?
Are we using back EMF, or would you use any kind of a trigger on these?
No, back EMF. So all of our ECMs are built with a permanent magnet rotor.
Yep.
So in the early days of drives, you may remember or have taught even Hall effect sensors where you've got a couple of pickups and those pickups, read how many times the motor goes past the pickups, and
Yeah.
it feeds back RPM. Well, our rotor being permanently magnetized is basically its own pickup, its own magnetic source, and then the windings of the stator are the pickups themselves, so they can read that back EMF as it goes around in the motor, and it knows its own operating RPM.
Awesome. Fantastic.
So again, hardwired at the motor. So unlike the indoor blower motors, no plugs. There's not going to be a 16-pin plug or a 9-pin plug or any external plugs, because that would be a source for water to intrude to the motor. Hardwired out. The wire colors, I should mention, are OEM specific. So I don't use any wire colors here, but if you learn on one particular brand of unit, don't apply those wire colors to, don't assume the blue and the yellow, for example, are always, speed and common. The wire colors could change from one manufacturer to another.
That's interesting. I've not encountered much of that because I've only worked with a couple different manufacturers. So I've been very consistent with what I've seen. And so I've not encountered variations of it. And that's very important to know when we're teaching about this.
Absolutely. And I haven't mentioned here, I have tried to be good about mentioning in other webcasts, we are not the only manufacturer of ECM motors today. If you go back about 10 years or so, we were the largest manufacturer, but there are other competitors today, and they also have different wire colors as well, different wire colors for their line and their low voltage. But I do want to say, as I've said in the other webcast, that probably 90% or more of what you're going to learn here will apply to my competitors' ECM outdoor fan motors as well.
Yeah, absolutely. It's understanding.
So last but not least, I do want to mention that these motors do have a 6,000 volt internal built-in surge protection. So it's not a surge protector component, so to speak, but it has a built-in components to allow it to handle 6,000 volts of surge. We get asked that question quite often, especially from certain regions of the U.S. where voltage and lightning and natural events seem to cause issues with that.
Sure.
It is built into the motor.
Okay,
so let's start out with one of the first and most common uses or types of uses of this motor, and that's the two-stage unit, because again, we said these are predominantly found in your 16-plus SEER systems. In your 16-plus SEER systems, you quite often start to see two-stage be the common design. Very, very few 16-plus SEER systems are single-stage, at least to my knowledge. And the most common usage of our motor in that design is what we call discrete 24-volt speed taps. So there's two speed taps, and again, they're not necessarily taps, they're wires. So I've got two speed wires, and they're activated by 24 volts AC. Like all of the other motors that we've discussed so far, these motors are powered continuously with line voltage. So the 208, 230 volt power to the motor is continuously powered.
Yeah.
Sorry?
L1, L2 is always hot on this one.
Yes, sir. And that could be back to the circuit board. That could be directly to the load side of the contactor, where as soon as the contactor pulls in, I've got line voltage directly to the motor. So that voltage is continuous. The voltage that's going to turn the motor on and tell it what speed to run in the case of our discrete 24-volt AC motors is 24 volts AC. So on this board, I've chosen the nomenclature Y1 and Y2. So if I'm in first stage, this board's going to energize 24 volts AC to the speed 1, and that 24 volts is going to go into the motor. The microprocessor is going to see that I've got 24 volts on speed 1. It's going to operate at whatever RPM the manufacturer programmed for speed 1 first stage. If it goes into second stage, one of two things could happen. When it goes into second stage, I could either terminate the voltage on speed 1 and energize the voltage on speed 2, or I could leave the voltage on speed 1 and add the voltage to speed 2. We've given the manufacturers the ability to do either or. So you could see them both energized, or you could see it switch from energizing one to the other. This is not like a PSC motor where you had to isolate speeds. You had to turn one speed off to turn another one on. Otherwise, you'd fail the motor. You can have both of them on at once. So that's another reason you need to get into the OEM manuals and find out, should I see voltage on both when I get to two-stage, or should I see voltage only on the second speed? But again, these are just 24-volt AC wires. and the speed that the motor operates at is dictated by the manufacturer of the appliance. You can see a little bit of the rating plate in this picture on the motor. That rating plate could say 850, it could say 1075, it could say 6 to 1200, it could say 1200, but really none of those numbers are 100% guaranteed to be what's programmed into the motor. That's how we tested the motor, how we UL tested the motor. We could then ship that motor to an OEM and they could program it to operate at 1 or 2 speeds that have nothing to do with the rating on the rating plate of that motor.
Could an OEM equipment, could they theoretically then run that as a 3-speed motor?
Thank you for the lead in there. I didn't even tell you to do that. Yeah, we need to have a rim shot audio ready there. So so yes, absolutely. So one option on the 2-wire 24-volt discrete speed motor is they can get a 3rd speed.
Yeah, I can see that.
And to get the 3rd speed, so you would get speed 1 by energizing wire 1. Whatever wire 1 is dictated as, whatever wire color it's dictated as. You'd get speed 2 by de-energizing wire 1 and energizing wire 2, or speed 2. And then you'd get speed 3 by energizing both at the same time.
Love it.
And in a 2-stage unit, most often that 3rd speed is used for some kind of low ambient mode.
Yeah, I got that. Yeah, and that's kind of what I was thinking about, because I've seen a wiring diagram before. I don't remember what manufacturer it was, but I remember seeing a 3-speed on an ECM motor, and I thought, well, that's with 2 signal wires, it makes sense. You just do 1 or 2 or 1 plus 2. So awesome. Thank you.
Yes, sir. And again, another reason to get in the manuals and find out how each manufacturer is operating that system.
Indeed.
So there are quite a few manufacturers. I was surprised as I started learning more about our outdoor fan motors and teaching them that there's quite a few manufacturers that use the ECM motor just at a single speed. And so in this case, where there's only 5 wires going to the motor, a line 1, line 2, ground, common, that's 4, and then your speed wire. And basically this motor spends its whole life looking for 24 volts on that 1 wire and turning on at 1 speed. And when that 24 volts goes away, the motor shuts off. The line voltage is there continuously, common's connected continuously, ground's connected to ground. The only thing that really changes for that motor is really I can reduce my engineers are probably cringing when they hear this, but I can reduce this whole complex motor to a simple relay. It's looking for 24 volts on that 1 wire to turn on and do what it's programmed to do. When that 24 volts goes away, the motor turns off. So once you understand how that motor works, especially in 24 volt discrete mode, it's a very simple motor to diagnose.
Very efficient.
It's not as easy to understand what RPM it should be running at if you're having refrigeration side challenges. But as far as the motor being on or off, it's pretty simple when it's using 24 volt speed or speeds taps. That's not a proper English there. Sorry. So any questions on the 24 volts before we move on to the dreaded PWM?
No, that's pretty good. I think this is a good time to see if anyone in the audience does have questions, because we really are talking quite a transition going from PSC into ECM, and then we're going to be getting into the PWM, pulse width modulation, which we've seen in our a variable, especially our constant airflow that's using a variable PWM, just to set the up or down stagings of our motor, but not in our condenser. And we are going to see a lot of that going forward. As we continue to have new energy expectations, we're going to have higher efficiency equipment. We're going to be making a lot more transitions into ECMs, whether it's in your blower, whether it's in your condenser, or whether it's in your compressor.
Yeah.
So it's really important to understand how they all function and how they're very similar, but yet there are differences in different types. And it's a good time. We've only had a few people, let us know where you're joining from. And we get that. Not everybody wants to say, hey, this is where I'm at. But I tell you one thing I would like to know from you. We have a new year, 2024. And we're so glad to have you here. And I know, it was a great time. We've all had, a lot of new learning lessons for this year. We've had 9 episode today. So we've had a couple of recaps along the waves. We have at least 66 new topics that we've talked about throughout the year. Going into 2024, I want to know what you would like for us to bring in. We've already got schedules out in through February of top educators that are going to bring, new things for us to learn about. But we also want to know, what do you want? this is for you. So make sure in that chat to let us know if there's topics that you would like to have covered, or if you have particular educators from the industry that you would like to see on the show to talk about things. And if you yourself, because there's a lot of educators out here, if you yourself would like to be on the show, let us know. We do ask that you would be a manufacturer trainer or a HVAC excellence certified subject matter expert. And if you are, let me know. cbeck@escogroup.org, and let's continue teaching each other. That's all.
Great stuff. Before I jump back into my presentation, I want to thank you for all the hard work and dedication you've given this industry. I mean, we desperately need it, and it's great to have this platform to come and talk on. And for those of you watching, I was not paid to say that.
That's right. We do this because we care and we love it.
Yeah, we do. We're kind of geeks about it, and that's okay.
Yes, it is. Okay.
All right. So switching gears to the dreaded PWM, and I say that very jokingly because every once in a while I get to do live classes.
Mm-hmm.
You can just see people like, oh, just kind of shrink in their seats when you mention PWM, because they're starting to hear more and more of it, and especially it's like anything, right? When we don't understand it, it's crazy. Once you finally understand it, in most cases, like, oh, that was easy. Why was I afraid of that?
Yeah.
And we've talked about PWM now twice in our first and second episodes on constant airflow and constant torque motors, and PWM is used here as well and is growing. So I would say up until, 5 years ago or so, most applications of our motors were used with just discrete 24-volt single or two-speed wires. But the PWM is growing because it's more versatile for the OEM. I'm giving away one of my slides, but that's fine. It's more versatile for the OEM. They have less skews, and they have a wider range of control of the motor. They can really program unlimited speeds. So in PWM, we have 5 wires. We still have the line 1, the line 2. We still have the ground, but we simply have 2 dedicated wires, and for PWM. And from what I have seen, most manufacturers will bring those wires back to terminals on the board that they actually label on the board PWM. I don't know if I made that square big enough, but that's the actual circuit board from a unit, and you can see PWM1 and PWM2. So it makes it very easy if you just follow the wires back from the motor and you see PWM1 and 2. Hey, that's an indication I need to get the manual out, because 1, you're not going to know what that voltage value should be, and 2, it will be a DC voltage value. Some technicians don't spend a lot of time clicking off of a VAC, and depending on what you're working on, you are going to need to spend more time on the DC side of your voltmeter as technology continues to evolve. So this motor can operate at 1 speed, 2 speed, 3 speed, or even more if needed. Again, 5 wires. The PWM signal determines the RPM. So not only is the volts DC, the PWM signal, the on command for the motor, but the value of that signal, the value of that DC voltage actually determines how much RPM the motor is going to run at. Higher voltage, higher PWM signal, the motor's going to run faster. Lower voltage, lower signal, the motor's going to run slower.
Okay.
I think you're laughing because this slide's coming.
No, so fun. I didn't even see it, but I love doing these classes with you.
So for those of you that haven't been to episode 1 or 2, or haven't had any introduction to PWM signal, basically it's a duty cycle. I can hear my 13-year-old son laughing. I said duty. It's a duty cycle, or what most people would look at that know the AC cycle. This looks like a half wave. And the idea is that if my duty cycle is longer, then the motor's being asked to run faster. If my duty cycle is shorter in relationship to time, so this time is 1 complete cycle. That's 1 cycle, repeated. The duty of that cycle, how long that cycle is on versus the entire cycle. And in this example, just to go a little deeper, in this example, this duty cycle is approximately 50% of the total cycle. So if the maximum RPM value of this motor was set to 1,000, and I'm using 1,000 just because I like round numbers when I'm teaching, so I don't have to math too much. If I'm at a 50% duty cycle, I'm asking the motor to run at 500 RPMs. Now, that's outside of the range I told you this motor runs at. It runs 600 to 1,200 RPMs. But if I have a motor set between 500 and 1,000, which is how motors, the PWM typically works. So the motor's told your minimum range is 500, your maximum range is 1,000. We just made up those numbers. 50% duty cycle would be the middle of that range. So the middle of 50 to 1,000 would be 750. So a 50% duty cycle wouldn't necessarily be 0 to the maximum value of the motor. It's whatever the min-max the manufacturer has programmed into that motor. So in PWM, the manufacturer doesn't have to program each motor and each motor speed individually for each unit. Really, all they program into the motor is the min-max value. So they can leave it wide open to the 6 to 1,200. They can skinny it up to 600 to 1,000. But whatever that min-max is, then the PWM signal, in this case, a 50% duty cycle, is going to be based on that min-max. So using all of that information as the example, the manufacturer can put all the programming in their board, and the motor skew and the motor programming can stay the same from one unit to the next. So it reduces the skews the motor manufacturer has to use. It increases the programming flexibility because it's all back in their motor. They don't have to program each motor as it comes down the line. And they also now have unlimited speed choices on the motor. If it's a two-stage system, they only need 2 speeds. They're kind of squandering all this wonderful value. But if they want to put a low ambient speed, they just program another PWM value. If they want to use this on a modulating system, and those are coming. No, they're not. They're here.
We're here.
They can simply modulate that PWM signal from the lowest end all the way up to the highest end to follow the demand of the compressor output of the system. So PWM is very easy, but what it really comes down to, and I don't know which slide I have coming up next. Nope. What it really comes down to for the technician is that PWM signal is developed by using DC voltage pulsed on and off, on and off. And it really, for those of you that are really, geeks in the electronic world, it really is like digital Morse code. I'm just pulsing that DC voltage on and off, and your DC voltmeter can read that value. So while I was one of the first people to go out and buy an anemometer, I was one of the first people to go out and buy a combustion analyzer. You don't necessarily need a PWM, a meter capable of reading PWM today, because manufacturers are recognizing that most technicians don't have it, and they're going to convert that to a DC voltage and say, if you see this DC voltage, the motor should be performing properly at first or second stage or low ambient.
Nice. All right. So it always comes back to understanding what's in the installation manual, knowing whether we have a 24 volt AC or whether we have a pulse width modulated that we would read with DC. And then it's just checking to see that we have high voltage and low voltage again. That's the beauty of understanding ECMs. If I don't have high voltage and I don't have low voltage, I'm not going to work. If I have high voltage and no low voltage, I'm not going to work. If I have low voltage and no high voltage, I'm not going to work. And it's understanding what those voltages look like.
You just knocked out my next 5 slides, but that's great. That's a great lead-in. Thank you. So there you go. So we're going to go right into installation setup and diagnostics.
Okay.
Installation setup is really easy. There isn't any. The board comes set up with the motor for either 1-speed or 2-speed or the low ambient, 3-speed operation. Unlike the indoor blower motors, where we have to select the correct heating speed for temperature rise, cooling speed for CFM, those speeds, those values, torque values or CFM values could change based on the static pressure of the system. We don't have those influences, right? We don't have ductwork on either side of the condensing unit, so we don't have to worry about that. It comes basically pre-set up from the factory. So let's talk about diagnostics. Diagnostics are going to be what you just said. It's going to be line voltage and low voltage. So we'll start off with the single or, before I start. Now, most of my images so far have shown a circuit board where the motor goes back to the circuit board. There will be some systems where when the motor connects to the board, it goes through a plug. If it goes through a plug, obviously we're going to have to get into the unit schematic on the door, Hopefully it's still there and legible, or I may have to go back to the manual to find out which wire color goes to what. Versus if they're individually wired, usually the terminal on the board is labeled Y1, Y2. It's pretty, or common. It's pretty easy to find out what those wires are. Also, there are some systems where there may or may not be a circuit board, and the motor might literally be wired directly to the contactor. The line voltage directly to the load, or even the line side of the contactor, and the low voltage, if it's 24-volt discrete speeds, literally connected directly to the thermostat wires that are coming into the outdoor unit from the indoor unit. So I wanted to cover that. I'm showing all circuit boards just because it's easier for diagram purposes, but you could see a hodgepodge of no circuit boards with contactors, or circuit boards with plugs. So I wanted to cover that quick before we dive into the diagnostics. All right. So let's start with single speed systems. You've already covered this, so I'm going to use the visual to cover the same information. You did a great job. I should just let you run this. You must have both voltages. I can't just have 230. I can't just have my 24 volts, in this case, single speed, 24-volt discrete speed. I have to have both. So if I only have one or the other, or if I don't have either, I have to go back to the HVAC system, find out where I lost it. If it's the 230, is my contactor not pulled in? Is my disconnect open? Do I have a fuse open? Whatever. If I don't have my 24 volts, do I not have the call from inside? Did I not make it through the circuit board? Some of these circuit boards are even tied into, and probably at 16 plus SEER, many of them are probably tied into low and high pressure switches, other safety controls. The fan and the compressor may be off because there's a compressor, what's the Copeland device, the compressor monitoring system. So, if I don't have that voltage, I'm going to have to go back into the system, find out where I lost it. Once I get both of those voltages back, if the motor's still not running, then I have a failed motor. And it's really just that simple. I provide tech support for our motors, and these motors, I spend the most time answering the same question over. Are you sure the motor's failed? You have both voltages going to the motor, it's not running. Yeah, but shouldn't it? It's just that simple. It's just those two voltages. I also get asked, well, should I separate the motor and ohm out the motor to see if the motor is good or bad? And the easy answer to that is you can if you want to, but I don't know of any OEMs that are selling the control-only replacement today in the outdoor fan motor. To my knowledge, they're all selling it as one complete part. Even the remote located ones, where it's the motor's remote located from the control, they still only sell it as one complete system, the motor and the control. So ohming out the motor is really a waste of your time, unless you just want to know, did my motor, which came first, the chicken or the egg? Did the control or the motor fail?
Yep. No,
so that's. Go ahead.
No, I my same way when I see what's out in the field and I see for replacement motors, all that I'm seeing are complete motor assemblies. I've yet to see a separated mod motor.
Yep. So again, before we change slides, if I have both inputs to the motor, in this case, it's a single speed motor. So I have 24 volts going to the single speed. If the motor's not running, the motor's failed. So switching gears to the 2-speed, if I'm in first stage, obviously I should have 24 volts on my first stage. But again, before we even get that far, I simply need both voltages for the motor to operate. Regardless of which stage I'm in, if the motor's not operating, I need two voltages. I need the line voltage and I need the low voltage for the motor to operate. If the motor is operating, if I have both voltages and the motor's not operating, the motor's failed. It doesn't matter if it's a 2-speed motor. If it doesn't work on one speed, that's going to be a problem, unless you're going to lock the system into second stage its whole life and wait for that second speed to fail, which is a question I have been asked. Well, what if my first stage speed doesn't work, but my second stage speed does?
Right.
Can I lock it into Y2 and leave it that way until I can come back and get cooling? Absolutely. If your second speed works,
okay.
That's not a problem. But keep in mind, that's probably not a good long-term solution.
No, it's temporary for sure.
Definitely a temporary solution.
Yeah, but I was wondering about that because if we, and from the technical side, I have not myself encountered one that has lost just one low voltage side of the circuit. It's either you lose it all or you don't. So have you seen any where you've actually lost one leg?
I have not on the outdoor fan, but I have on the constant torque indoor blower motor where it has the
Okay.
5-speed taps. I have had technicians report to me that one tap stopped working and the other still worked. Each one of these taps, when they're in 24-volt discrete mode, the taps internally have something called an opto-isolator. And what that means is there's an optocoupler between where the 24 volts comes into the motor
Mhm.
and where that signal actually makes it to the micro.
Oh,
It's sort of
okay.
a safety circuit.
Yeah.
So it is possible for one speed to have something blown that doesn't allow that signal to make it to the micro, and another speed to still work.
Interesting.
Um,
Okay.
Again, in most cases, like you said, the motor either works on all speeds or it doesn't work on any speeds.
Right.
But that's a question that I have been asked, so I thought it was worth bringing up here.
Yeah, absolutely.
Yep. So now that we're on the 2-speed motor, and this bit of conversation will apply to the PWM motor as well. If I do have a system that seems to be underperforming, and this is where we're going to maybe talk a little bit about the refrigeration side of the system. So let's say my superheat and my subcool aren't aligning.
Mhm.
My head pressure switch is tripping. Maybe I'm just throwing out some refrigeration side what ifs. That's where it might be valuable to know that this is a 2-speed motor, and you may be on first speed, first stage speed, but you may be in second stage operation, right? So if I'm in second stage compressor, but my motor's only operating on first speed, maybe the wire fell off of the
Mhm.
Y2 there. Who knows why the second speed didn't, or maybe the second speed doesn't work. Very rare, but possible. It's good to understand that one, is this particular system going to switch from Y1 to Y2, or is it going to energize both? And secondly, do I have the Y2 value on, right? There's technicians in the southern regions logged in right now that are probably like, this is so common sense, Chris. Why are you even talking about this? But, there's technicians that have not worked on these motors at
Right.
all
Yeah.
and wouldn't even think about the idea, and maybe never worked on, those really old systems that had the 2-speed PSC motors with the rheostat's
Right.
not the right word, but that thermal sensor in the outdoor unit. Um, if I'm stuck in the first speed operation, but I'm in second stage compressor, that's like having a really dirty coil.
Yeah.
And
Absolutely.
you might be trying to diagnose it with refrigerant or airflow through the coil, and it could simply be you're not operating in second stage speed on the motor as well. So if you have anything to add to that, please feel free.
No, the only thing I could think of is I can see the manufacturers of the boards utilizing relays to be able to make the connections to the speeds for the outdoor motor so that you wouldn't have the potential for overloading your low voltage circuit for the entire system. So I could see potentially you could have a relay failed. Say you had a Y2 relay on the board that failed and you had a Y2 signal coming into the board, but not a Y2 signal coming out of the board going to the motor. So just something to think about when we're troubleshooting those, speed connections.
Yep. Yeah, and I bring that specific scenario up because one of the very few calls I do get on these outdoor fan motors, the technician was having that struggle.
No.
They were it was tripping on high head pressure. It was acting like a dirty coil. It was acting like other refrigeration issues, and so we went through the motor and we found out that the Y2 wire had fallen off.
Look at that.
And it was literally just that simple. And the technician just didn't think, since the motor was running,
Yeah.
never thought about the fact that it could not be running in its
On the right
second
speed.
stage capability.
Love it. Love
Yeah.
it. Great example.
Yeah. So switching to switching to second stage, we've got the same diagnostics, except you may or may not have noticed. I'll rock back and forth here that
Mhm.
I've moved my meter over to the Y2. Again, we need both voltages for the motor to operate in Y2. And again, I'll reiterate, some systems, it may turn off Y1 and bring on Y2. Other systems may energize both. And on some systems, energizing both could be a third speed. So you may want to get into the manual before you start jumping terminals together, thinking it needs both of them.
Great.
All right, so PWM. Again, hopefully if you've watched any of the other webinars that I've done with Clifton, or by the end of this one, you don't feel like PWM is a dirty 3-letter word anymore. And understand that it's really quite simple. PWM signal, again, as I mentioned earlier, it's a duty cycle, but it's created by a DC voltage. You're simply going to switch your motor to DC volts. And probably the most cumbersome part about diagnosing a PWM system is there's no one set of values. It's not the atypical 24 volts AC, or what you may see on some systems, 18 volts DC is a very common DC signal voltage that gets used. This PWM signal voltage could literally be anywhere from 2 to around 20 volts DC, and don't write that down and say, okay, it's always going to be between 2 and 20 volts DC. It could be a little lower, it could be a little higher. It's all dependent on how the OEM wants to develop that signal. So this signal really is dependent on you getting that OEM manual out, finding that diagram or chart or paragraph that says stage 1, you should see 2.2 volts DC. Stage 2, you should see 3.5 volts DC. Again, those were examples. Don't write those down. And then simply applying your meter to those PWM 1 and 2 pins and measuring that DC voltage. So whatever that value is, let's say it's 2.5. I put my meter on there. I have 230 volts. Whoops, sorry. I have 230 volts and I have my correct DC voltage. The motor should be operating. And if that voltage is what the manual says it should be for either first or second stage, that also means I should have the correct airflow for whatever stage I am in. Many manufacturers with PWM will also provide a low ambient speed, and that's going to again be typically a lower PWM or DC volt value than your first stage. So if you do have a low ambient controls and you're in low ambient mode, be aware. I say that because you may get comfortable after you start measuring these, seeing say 2 point something DC for first stage and 3 point something DC for second stage, and then you'll go on one. You'll have 1.5 and think, well, that's not right. Something must be wrong, but the motor's running, and think, well, the motor must be bad or the board must be bad. It might just be a low ambient staging that it's in versus something actually being wrong with the motor or the control.
Fantastic point. Yeah, especially up north. I see that be common. I mean,
exactly.
We have businesses run air conditioning year round, even if it's snowing.
Right. Well, maybe not this year because we still haven't had snow yet.
No, we haven't either. Just a little bit of a dusting, but not very.
Yeah. Anything you want to add on PWM before we leave that?
No, that's great, especially the low ambient. A lot of people don't realize that it's just that easy with an ECM. That's why I love these motors. When we first were introduced to ECM and variable speed, we're like, oh man, these are animals we have to learn, and we're going to have special tools and scanners, and we're going to have to have an oscilloscope on the van at some point. No, it's nothing like that. It's just knowing what they're designed for. And we all have a very similar design, similar concept, but we do that in different fashions. So it becomes very OEM specific. What did the manufacturer decide to do with this product? And that's really what we're here to do, to break them down, take the fog off and go, oh, that's all it's there. That's pretty neat.
Yep. And since you said all that, I'll say it's also a good time to reiterate RTFM, read the full manual. If you want to show up to systems and not show up and look at the system and see the big monster with the ECM and go, if you want to show up and go, I got this.
I know you.
Exactly. The more you read the manuals, and if I haven't said this in previous webcasts, some of these manuals, and I should have had one out, but some of these manuals are 40, 50, 60 some pages. But after you read 1, 2, or 3 manuals, what you're going to find out, there you go. When you, especially if it's just the motor operation, it's the same 3 pages, in any manual. You're looking for the performance charts, you're looking for the diagnostics for either the PWM signals or what the tap terminal designations are, if it's not on the door on the schematic. You'll find yourself, especially if you get PDFs, you'll find yourself like me, just scrolling until you see that page with all the performance charts on it, or the wiring diagram. That's exactly what you need. And while a minute ago I said don't get too comfortable with numbers or wire colors, don't apply them from one system to the other. Once you start getting comfortable with those pages in the manual, these systems will become so easy and comfortable for you to work on. You'll laugh at how much you used to cringe when you saw them. At least that's been my experience.
No, I absolutely agree with that. I get into these conversations all the time, and people start talking about wiring, and I go, "You realize that every wire in your manual is gray, don't you?" And actually, I was doing a wiring class one time, and I had a gentleman in the class, and we were just breezing through the entire presentation. I mean, he was just nailing everything. And one of the guys got hung up on a wire color, and the guy raised his hand. He's sitting in the back, and he said, "I'm colorblind. Why don't you see it?" And the whole class stopped, and I went, "We need to talk about this," because my dad was colorblind, and I completely get it. They're all shades of gray. It's a matter of starting and finishing, following the path. Does it really matter what color they are? It's a matter of finding out where they land and what they do. And so when we understand what they do, then it's a matter of just locating what those labels are on our diagram. So,
Yep.
Great stuff.
Yep, opens up the whole world. And I'll take that one step further, since we're being total nerds here, and say that for me, when I first started, when schematics first started making complete sense to me, when they weren't just hieroglyphics, when I started getting into manuals, it was almost like the day that just reading as a child became simple, and then all of a sudden the whole world of literature opened up to me. For me in HVAC, that's how schematics and manuals were. Once I understood schematics, once I finally forced myself to read the manuals, I just felt like somebody took the cloth over my eyes, and everything made complete sense. So I don't want to belabor that too much. You and I could beat that pickleball back and forth. I see there's a couple of questions out there.
Yeah, one probably needs to be addressed, or at least touched on a little bit, because we can all relate to the old days of ECMs.
Yep. So I'll hit that one. The one from Robert White about some manufacturers say you can use a 9-volt battery to temporarily run a motor that has a DC signal. Does that apply here? That was a practice, and I won't call out the manufacturer for it, but that was a practice that one OEM recommended for diagnosing the constant airflow variable speed motors a long time ago. Couple of challenges with that practice. One, if other technicians are like myself, where the only 9-volt battery on the truck is the one that's barely alive inside my voltmeter, that's going to be a challenge, because I will need a good 9-volt battery for it. There's also a certain amount of taping and wiring to get the right wires on the terminals. So I would say that that one manufacturer figured out that it worked on their motor because they knew how their engineers programmed it. I don't think it's going to apply very well to these outdoor fan motors, especially the ones that are in PWM. So I would suggest not using that trick on outdoor fan motors. But as I will say, with any question that's asked of me that I don't know unequivocally the answer to, prove me wrong. If you find one that works, take a video, send it to me, and prove me wrong. But as far as I know today, the answer is no, that practice doesn't work. And someone else said 1 out of 8 adults are colorblind. So another
from Howard. Thank you.
Another good reason to understand and comprehend both sides of the schematic. So again, not to get too nerdy here, but schematics have the pictorial and they have the ladder diagram. And the purpose of the pictorial is that it more accurately represents where the components and the wires are in the system, so you can sometimes follow the wire from point A to point B and not necessarily have to see what color it is. So very good point there, and thank you for bringing it up.
Yeah, man, lots and lots of great stuff here.
You betcha. So again, we talked about the AC and the DC volts. Must have both. And for the DC voltage, we will need to get that from the manufacturer. And the first one you measure, don't write those numbers down and assume those are going to be the same DC voltage from one OEM to another, or even from one OEM system to another. So, for example, if I'm working on I'll just use a manufacturer's name. If I'm working on a Train split system, 16 plus SEER, and I measure the DC voltages, and I go to a Train package unit, those DC voltages could be different. They could run that motor at a different RPM value, even though it looks like the same motor, same horsepower, could even be the same Gentech model number on that motor. They could send a different PWM signal to that motor because it's in a different application.
Different prop, even just a prop angle. I mean, I've seen applications where we've had a manufacturer change suppliers of blades. and then in the middle go, oh, what should we do? Well,
Yeah.
with
Yeah. And I believe, if I'm not mistaken, many of them are making their own blades now because since ECM, and I say since ECM, which is 22 years ago, since ECM, they can now develop the blade any way they want to, right? The blade manufacturer has more flexibility in the design of the blade than they did before, because before ECM, it was, you got to make it work at 825 or 1075. That's it.
Right.
I mean, you could run it at 1625 if you want to, but that's going to be really noisy sitting next to the bedroom window.
Exactly.
So, they were stuck with those two operating points. Now they've got 600 to 1200 RPM to play with. They can make that blade as quiet as possible, and not just decibels. Just because I like to say the word womp womp. They get rid of that womp womp sound with the blade, and that makes a very big audible difference to that entire unit.
Yeah, absolutely. And that's something that a lot of our manufacturers are paying more attention to, is the quality of the atmosphere around the outside unit. So we are producing a lot of quieter systems.
Absolutely. So that leads us into the, I think is the final slide for this presentation, which is replacement. So if we do find we have a failed outdoor ECM fan motor, today you do need to go back to the OEM if you want to get exactly what was there. So technicians can do whatever they want to do. They can install a PSC motor. They can install, we make some evergreen outdoor fan motors, but those evergreen outdoor fan motors are designed to replace PSC motors. They're not designed to replace ECM outdoor fan motors. They look exactly alike, but they're not designed today yet to replace ECM outdoor fan motors. They're only designed for replacing PSE. So if you have a failed ECM outdoor fan motor, if you want to get exactly what was there, you want it to be plug for plug, plug and play, you want it to operate exactly like the original motor, you do have to go back to the OEM. And the biggest, again, we brought this up a little bit earlier, but I do want to revisit this. The biggest challenge is the RPM on that rating plate of the failed OEM outdoor motor is not always, and in many cases, not going to be indicative of the programmed operating point or operating points of that motor.
Yeah, makes sense completely.
And so, it may say 850 or 1075 on the side of the motor, but that may be one of the operating points. What's the first stage or operating point? Or maybe that 850 was how it was tested, and the manufacturer is choosing to run it at 950 and 1000. You just don't know. I have been getting reports that technicians are replacing these with PSC motors when the OEM motor is not available. It's 100 degrees in Dallas. The customer's not going to wait 2 weeks for a motor. If it's not available, technicians are putting in PSC motors. And for that, I'll simply say, be careful of what you're putting in. If you put in the wrong motor, you could affect the efficiency of the appliance, which may or may not be so bad as long as you're still getting cooling, but you could also affect the longevity of the motor if you put in a higher RPM motor than what was there.
Yeah, indeed. Back to the OEM. And they're really not incredibly expensive. That's the beauty of these ECMs. As they're becoming more popular, we're starting to use them in lots and lots of new equipment. The prices have really become very competitive with our PSC motors. So, if you have a PSC motor and ECM that are similar in prices, and why? why would you want to put in a motor that is going to fail under a heavy load versus an ECM?
Yeah, and the biggest challenges I see there are that, one, if it's not available that day, that just like when it's 10 below in Wisconsin, we have to get the system running as soon as possible. When it's 100 degrees in Dallas or Miami or wherever, or Phoenix, you can't. That customer is not going to wait weeks or even days if they don't have to. So the technicians want to get something in there to run it. And the price point, not to contradict what you said, but I have been hearing that price point, at least on the outdoor fan motors, has not been coming down as much as it has on the indoor motors. You're very right about the indoor motors, and I think that's been because of the universal motor competition.
Yep.
But in the outdoor fan motors, to my knowledge, there's no universal replacement competition yet today. So that the two complaints that I hear most are availability and price.
Okay, no, that completely makes sense. I'm glad you pointed that out, because that absolutely makes sense. Great stuff. We still have a lot of people out there. In the app. Yeah.
So yeah, if you'll permit me, for anyone that may not have watched the first 2 episodes, I do want to mention, we have an app. Everybody has an app. I was given some flexibility in building our app as a former technician. I wanted to have an app that would benefit the technicians in the field. It does help with cross-referencing motors. It does give you diagnostic information. A lot of the diagnostic information we covered here is covered in the app for our OEM and our aftermarket motors. We do have distributor locators and PSC replacement guides as well. All of our training, all of our videos, all of our manuals. If anyone remembers the old Fasco Facts for induction motors, I myself learned almost everything I knew about induction motors before I came to work for Regal Rexnord from Fasco Facts. That piece of literature is now a PDF. It's in our literature library. All of our podcasts, these webcasts, will be in our training center, and you can access that all from your phone. So if you're on a lunch break or if you're in between jobs, you can do a little bit of training. The Evergreen VS Optimizer was covered in episode 1.
Mm-hmm.
So I'll let people go back and watch that. That's a little reason to go back and watch episode 1. There you go.
Mm-hmm.
And our Evergreen tech support for our Evergreen universal motors. If you're on the job and need a manual, need a installation video, those are all just one click away. In the tab on your phone. If you like to work online, if you like to work on your small laptop or tablet on your in your truck, all of this is also available on the website, the Dealer Tool Box. So the app is called the Dealer Tool Belt. The website is called the Dealer Tool Box. They are mirror images of each other with all the same information. If you're online, the direct link to our training page with all that great training is regalmmu.com. And a shameless plug for my book that is still available through ESCO, Understanding Electronically Commutating Motors. If you're a complete geek or you just struggle from insomnia, you'll get this book and it'll put you right to sleep. You'll never get past chapter 2, trust me. And if you want more hands-on knowledge in the book, you can go ahead and skip to chapters 3, 4, and 5, where it'll cover a lot of the same information that we've covered here. The hands-on information for constant torque, constant airflow, and constant speed motors. The earlier chapters cover more of the theory, which I find valuable.
Mm-hmm.
I was that kid that tore stuff apart to figure out how it works.
Right.
May or may not have always got it back together working, but I did understand how it worked after I tore it apart. And so with that, I will say that's the end of the information I have to give you, and I'll turn it back over to you, Clifton.
Oh, no, that is fantastic. And Chris, we really look forward to seeing you at the National HVACR Education Conference. We encourage everyone to join us there. And, I got to go back. So we were talking about tearing things apart, as kids. And we're just big kids. We still tear stuff apart, right? So last night, our oldest daughter is doing the little glitter nail polish, right? Her and her friends in the living room. It's got glitter. And she says, "Have you got a magnet?" I'm like, "Have I got a magnet? You ever seen an ECM rotor before?"
Uh-oh.
So I was able to reutilize our tore apart ECM from last month's show to make a really nice handheld magnetic club.
Very nice. I'll have to send you some neodymium magnets from the new rotors. They are 10 times more strong.
Oh, I want one so bad. Yeah, I will reconnect with you on that one for sure. And, and speaking of like neodymium and new technologies, these are the things that we are looking for from you. What would you like to learn about going into 2024? And we will make sure that happens. So for anyone that wants to reach out to me, please give me a ring, give me a shout, send me an email, cbeck@escogroup.org. And I'm really looking forward to 2024 and all the things that we get to do together.
Couldn't think of a better way to start it off. Thanks for having me again, Clifton.
Absolutely. We sure appreciate you so much. We appreciate everything that Regal Rexnord does for training the industry and bringing these technologies and just makes them comfortable for all of us, whether we are a technician, whether we are a installation or service manager, whether we are a contractor, an educator, a distributor. We all have the opportunity to learn and grow together. All right.
Sounds good to me.
I think that's it. That's a wrap. We will see you all again next week on Did You Know, the ESCO HVAC show, where I dive into mitigation. What is mitigation?
Ooh.
Anybody know what mitigation is?
I'm not even going to try. I'll mess it up.
It'll be fun. All right. Well, we will see you all again.
Have a good night.
Thank you, sir.